Okay, we have returned an interesting integral. We've got the integral from 0 to 1 of sine ln x over ln x dx. Okay, I've been noticing that it seems like every integral I do lately has got a sign in the numerator and something in the denominator. So I'm going to have to try to mix it up a little bit more, but let's just get started with this. So first, noticing we've got ln x in the numerator and denominator, let's do a u substitution for that. But instead of just doing it for u equal to ln x, let's get a minus sign in there, just because if I rearrange this and I have minus u equals ln x, and then I solve for x, we get x is equal to e minus u. It probably doesn't really matter, but a lot of times it's more convenient to have this e to the minus u. So I'll take a derivative on it. So dx is going to be minus e minus u du. Go ahead and substitute. So when we plug in 1, ln 1 is 0. Plug in 0. ln 0 is minus infinity times minus gives me a positive infinity. And then on this part, let's actually just create a minus sign on here, just so that we have this is exactly u. I can do the same thing here, create a minus sign in the numerator, so I'm not changing it. But then, because sine's an odd function, I can just multiply that minus sign in and get it in here. So then when we do our substitution, what we're going to have is now we've got sine u in the numerator. This is just u. dx is going to be minus e minus u du. Take a minus sign and we'll use that to flip our bounds around. But now let's actually just parameterize this. So on e to the minus u, let me rewrite this. I can write this, I can create a parameter s right here in the exponent. And then let's just call this whole thing f of s. And then this thing here is perfectly in our form for a Laplace transform. This is going to be the same thing as just Laplace transform of sine u over u. For this Laplace transform, we have a couple of formulas we can use. We have something for sine of at. This is going to be just the same thing as s squared plus a squared with a in the numerator. And then for something in this form where we're dividing by the variable here u or t or whatever, we've got a nice formula for this. If we have something in the form f of t over t, this is going to be expressed as an integral from s to infinity of big F of u du, where this thing is actually just the Laplace transform of f of t. So this is going to be the same thing as the Laplace transform of f of t. So for this part here, we have our formula. We can say for the Laplace transform of sine of u, that's just going to be u over s squared plus our coefficient's 1. So 1 squared is just 1 using that. Sorry, this is a mistake. This should be a 1 because in the formula we got the same a value, the coefficient here and here. And so then what we'll use for the Laplace of sine u over u, we just want this formula here. So what we have is this is going to become s to infinity du, turning this, we're changing the variable into u. I mean, really, it's a definite integral, so I can change this into whatever we want, but let's use u. So when we do this, now we have du over u squared plus 1. This here is just the arctan formula. So when we integrate this, we're going to have arctan of u evaluated from s to infinity. Plug in infinity, we get pi over 2. Plug in s, we get minus arctan of s. I do have videos on all these Laplace transforms. I'll put that in the description. We have a video for this exact one, but we also have it for this one and this one. But anyway, in this one, I think what I forgot, or no, actually probably in this one. Yeah, in this video, one thing I forgot to say is there is a nice formula that if you have arctan of, let's say s for now, this doesn't matter. If you have arctan plus cotangent, this is the same thing as pi over 2. And in this case, there's no restrictions on s. When you have the other formula arctan of 1 over s, then it's only for positive numbers, but this works for any s. So then just rearranging this, if I subtract arctan on both sides, we have pi over 2 minus arctan of s equals arc cotangent of s. So what that means is I can write this whole thing as arc cotangent of s. I don't know if it's better this way because a lot of people are more familiar, but we have this other way to express it. So now what we have here is this is just our f of s value, either of these. And so going back to the parameter, what we did here is we just threw that s value in there. And what we're doing, I should have mentioned it before, we're saying here s is going to just be equal to 1. That way we don't change it. And so our solution, so what we want for our solution is just going to be f of 1. So for f of 1, whether you use arctan or arccotangent, it's the same value. It's pi over 4 in both cases. So let's use the second one. So for my final solution of this, we just get pi over 4. Okay, there you have it. That's it for today. Thanks everyone for watching. Have a good day.